the second lesson, Angles in Unit Circle, of Chapter 13, but this is the second day of the notes. So what we're going to do today is we're just going to begin with what the definition of the unit circle is, and then we're going to review some special right triangle information from geometry that we will need when we build the unit circle. And we're going to build the unit circle together in class, and then you'll understand more about why we needed the special right triangle stuff. We're just going to practice it today. We're not going to really tie it to anything until we build our unit circle in class. So the unit circle is a special circle because it has a radius of 1 always. Okay, radius of 1. Radius equals 1. So that means that the distance from the center to the outside edge of the circle, no matter where it is 1. Okay, the radius is 1. And the origin, of course, is at the center of the circle. So that's the origin in the very center. So this is quadrant 1, quadrant 2, 3, and 4. Okay? So other points about the unit circle are that the points making up the circle directly relate to the periodic functions for the sine and the cosine. So let's just write this first, and then we'll talk a little bit about it after. The points making up the circle directly relate to the periodic function for sine and cosine. Now, when we get a little further into the chapter, when we get a little further into our understanding of the unit circle, we're also going to study the periodic sine wave and cosine wave. And that is because they are directly tied to our unit circle. And so I'm going to show you a couple of videos in a little while when we study sine and cosine that pretty much unwind the unit circle and show you how it turns into a sine wave or a cosine wave. And then hopefully that will make the connection between the two a little clearer for you. Right now we're just kind of doing the basics, learning the characteristics of these things, and then we're going to apply them to sine and cosine waves later in the chapter. So I'm going to draw you this angle. Right? So any angle we draw on the circle is going to have this point. Okay? And that point is an ordered pair. Because remember, the circle is like overlaid on your Cartesian coordinate plane. And so in quadrant 1 or any of the quadrants, when that line, that ray, crosses the circle, it is an ordered pair. So I would have to go over some x value and go up some y value to get to that point. The x value relates to the cosine of the angle, and the y value relates to the sine of that particular angle. So we'll call the angle theta. That's the Greek letter theta. It kind of looks like a cursive O. Okay? So angle theta has the point cosine sine on the outside edge of the circle. So this represents the x, and this represents the y. And we get those values by doing the cosine of that angle and the sine of that angle. Again, when we build our unit circle in class, it's going to make a little bit more sense to you how we're getting those numbers, okay? How I remember which one goes first and which one goes second is that C comes before S in the alphabet. So cosine goes first, sine goes second, okay? So the cosine and sine of an angle means the x coordinate and the y coordinate. They correspond, okay? So that's essentially all we're going to talk about when it comes to the circle today, is just that. That's the theta. It has a radius of 1, and then the points all along the outside of the circle formed by that angle are cosine and sine. That's how you get your x value and your y value. So we're just going to review special right triangles. I'm going to ask you to pull my page, and you're going to prepare to write in these two triangles. So think way back to geometry. And imagine that this is a 45, 45, 90 triangle. So this is the special right triangle, 45, 45, 90. We know that in a 45, 45, 90, we have an isosceles triangle. So we know these two legs are congruent to each other. And so remember we labeled them n and n. They were equal to each other. The hypotenuse was always n square roots of 2. Okay? N square roots of 2. So n, and n square roots of 2. So 30, 60, 90. What's the other special right triangle? Now remember these labels that we're putting on the sides are the relationships among the side lengths of those triangles, okay? So across from the 30 is your n. The hypotenuse is always twice the short leg, or twice that side. And then the third side is always n times the square root of 3. These are given, proven relationships. So we always use these as like a rule. So we're going to do a little practice, kind of solving for missing sides of these triangles by using these relationships. But before we do that, let's also review rationalizing the denominator, because we know that the denominator needs to be a rational number. So right now, the denominators are irrational numbers. So we have square root of 5 and square root of 4. We're not allowed to have those, so we need to rationalize the denominator, okay? So by rationalizing the denominator, and you'll remember this because we just finished this chapter, we are going to multiply by the square root of 5 because we want to get the square root of 5 squared. And by having 5 squared, right, we know that a perfect square under a square root cancels each other out, and we are left with just 5 in the denominator, so we've rationalized our denominator. If we multiply the denominator of our fraction by the square root of 5, we also must multiply our numerator by the square root of 5, and so when you multiply that together, you get 5 square roots of 5, and I've already simplified my denominator to 5, so I'm just going to drag the 4 square roots of 5 over, and there is nothing else I can simplify because the two coefficients outside the radical, 4 and 5, are not simplifiable by the same number, so we're done. We rationalized the denominator, okay? Now, I know that some of you are looking at the second example and saying, Mrs. Pelletier, the square root of 4 is 2. I already know that. And you can put your 2 in the denominator, and that's great. But let's just practice the process of rationalizing using a root. So I'm going to multiply by the square root of 4, and that's going to give me the square root of 4 squared. And I know that those are going to cancel each other out, and I'm going to get 4 in the denominator. Okay? So I want you just to pretend. And then I'm going to have 12 square roots of 3. Okay. And then I'm just dragging that over. Oh, I'm sorry. Hang on. Let me fix this for you. That's not what I meant to write. I'm doing two things at once, which is not always good. So again, multiply the denominator by the square root of 4, multiply the numerator by the square root of 4. So now I'm going to multiply across the top, and I get 12 square roots of 12. Okay, and I have to simplify my square root of 12. Now remember, I already have a 12 out in front. So 6 and 2, 2 and 3. I need a group of 2 under my radical. I'm going to rewrite this. This 3 is going to hang out all by itself. So I'm going to have a 12. This is the 12 that I already have. I just carried it over. Square roots of, here's my 2 squared, and my 3 left over. So a perfect radical, perfect square under a square root cancel, which means the 2 comes out. So 12 times 2, square roots of 3. 12 times 2 is 24, square roots of 3. So I'm going to replace that. It's 24 square roots of 3. And then these can be simplified. 24 divided by 4 is 6 square roots of 3. Okay? Now, if you had just taken the square root of 4 and gotten 2 in your denominator with 12 square roots of 3 in the numerator, you would also see that that simplifies to 6 square roots of 3. So yes, you could have done it the shortcut way. I just wanted you to practice using that method because, as I said before, some students have trouble recognizing perfect squares under the radical. So this multiplying by what you see here is a surefire way to get yourself to the answer without having to necessarily know all of your perfect squares. If you know your perfect square, fabulous, you're ready to go. So we're going to scroll to the next page and do some practice simplifying some triangles. So, looking at the top of the second page, use the given information to find the missing side lengths in each 45, 45, 90 triangle. Rationalize the denominator if needed. So, we have a hypotenuse of 1. So this is a 45, 45. Okay, 45, 45, 90, and the hypotenuse is 1. So, back in geometry, when you did this, you had to go ahead and label the sides with the relationship. So this is n, this is n, and this side that we know is equal to 1 is also equal to n square roots of 2. They represent the same side. And so what we have to do now is we have to solve to figure out what these two sides that are labeled n are equal to. And we have to use this equation to do it. So I'm going to write this down here. To get n by itself, I'm going to divide by the square root of 2. And if I do that to one side of the equation, I have to do it to the other. And now I know that I cannot have a radical in the denominator. So I'm going to have to rationalize that denominator. So I'm going to take and multiply by the square root of 2. And I'm just working to the left because I'm running out of space over here. And so I'm multiplying across the top, square root of 2. And I'm multiplying across the bottom. Any root times itself is the number, because I'm going to have 2 squared under the square root, and those are inverses. So the square root of 2 over 2. So n equals the square root of 2 over 2. And this side is also equal to the square root of 2 over 2. So there are our 3 sides. When someone would ask, what are the relationships among all 3 sides, you would say, well, this leg is the square root of 2 over 2, this leg is the square root of 2 over 2, and this leg is equal to 1. Okay? Second example, we have a triangle that has a leg of 2. So, again, it's a 45, 45. They told us that in the directions. 45, 45, and a leg that is 2. So again, remember that if one leg is 2, both of the legs have to be 2, because they're equal. This is an isosceles triangle. So I'm just going to first label my sides n, n, and n square roots of 2. And so then I look around and I ask myself, do I know what n is equal to? Yes, I do. It is equal to 2. So I'm going to take this 2 that I just got, n equals 2, and I'm going to plug it in for all my other n's. n is 2, and 2 square roots of 2. So now if I ask you what are the lengths of all 3 sides of this triangle, you would say that leg is 2, that leg is 2, and the hypotenuse is 2 square roots of 2. So you are labeling, matching your sides, and solving. Let's look at the third one. Hypotenuse is 1. Okay, so 45, 45, 90, hypotenuse is 1. Notice anything similar, right? So we already done this one in example 1. We did it with 1 inch, and now it's 1 feet. Same exact thing. N, and n square roots of 2. We just simplified that a few minutes ago, right over there. And so we know that these other 2 sides are the square root of 2 over 2. This one is also the square root of 2 over 2, and the third side is 1. Okay? So some practice with the 45, 45. Now let's practice some with the 30, 60, 90. We won't be doing a lot of this when we build our circle. I just need you to recall, think back to what what these triangles look like and how we got the side lengths to them. We're not going to actually be solving them. Once we build our unit circle, we will just know what those areas of the circle are all equal to, and we won't have to actually calculate it every single time. But when we build it, we're going to be calculating it out for the first time, so you understand where those numbers come from. Okay, so that's why I'm just reviewing this with you. We're going to use this to build our triangle. our unit circle. So this time we're dealing with a 30, 60, 90. 30, 60, and 90, and the hypotenuse is 1. So let's label our side. Across from the 30 is n. The hypotenuse is 2n, and the third side is n square root of 3. And now we just need to look around and decide what we're going to do to solve. So this looks like my equation that I will solve. 2n equals 1. To get n by itself, I have to divide by 2. Divide one side of the equation by 2, then you have to divide the other side by 2. So n equals 1/2. So this side equals 1/2, and this side equals 1/2. Okay? So if I ask you what are the lengths of all three sides, you would say the hypotenuse is 1, the long leg is 1/2 the square root of 3, and the short leg is 1/2. You have all three sides. Okay? This one, again, draw your 30, 60, 90, 30, 60, and 90. The short leg is 3. And I'm going to label my sides with my relationship. Okay? Across from the 30 is n, the hypotenuse is 2n, and the third side is n square root of 3. So, you're going to look around the circle. You're going to ask yourself, do you know what n is equal to? The answer is yes. N is equal to 3. So now it's just plugging it in. So 2 times 3 gives me a side length of 6. And then 2 times the square root of, 3 times the square root of 3 is that side. So again, do you know what all three side lengths are? Yes, the hypotenuse is 6. The long leg is 3 square roots of 3, and the short leg is 3. So again, you have what all three sides are equal to. Number 3. Now your 30, 60, 90. The long leg is equal to 4. Label your sides with all of your relationship. Across from 30 is n. Hypotenuse is 2n. And the long leg is n square root of 3. So I'm going to have to solve that equation, which again, I'll write it down here, out of the way a little bit. N times the square root of 3 is equal to 4. I'm going to divide by the square root of 3 to get n by itself. If you divide one side of the equation by the square root of 3, you've got to divide the other side by the square root of 3. And now I'm just looking at this thinking, I can't have a radical in the denominator, so I need to multiply by the square root of 3 so that I will have the square root of 3 squared. Those are inverses, and they undo each other, leaving us with just the number 3. If you multiply the denominator by the square root of 3, you have to multiply the numerator by the square root of 3. 4 times the square root of 3 is 4 square roots of 3. And again, you just slide that over. And you are not able to divide 4 and 3 by the same amount. So you're just going to go ahead and leave it. So I have n is 4 square roots of 3. So now everywhere on my side length, I need to put in 4 square roots of 3 over 3. Here I have 2 times that. I'm doubling it. So now I have 2 times 4 square roots of 3 over 3, which is going to give me 8 square roots of 3 over 3. So if I asked you what all three side lengths were, you would tell me this side is 4 square roots of 3 over 3. You would tell me the long leg is equal to 4, and you would tell me the short leg is 8 square roots of 3 over 3. So we have all three side lengths. So that is your special right triangle review, and also just a very small, super easy look at what a unit circle looks like.